today we're going to introduce the concept of effective gravity. We know that from Newton's law of gravitation that the force of gravity divided by the mass is equal to the acceleration of due to gravity, which is the gravitational constant times the mass of the object, in this case the mass of the Earth, divided by the radius, the distance from the center of that mass. For the Earth system, our gravity constant, 6.67 times 10 to the minus 11th. The mass of the Earth is 5.972 times 10 to the 24th kilograms, and the radius of the Earth the average radius is 6.367 times 10 to the 6 meters. If you put those numbers into this Newtonian form of gravity, you'll get a gravity at the Earth's surface of 9.826 meters per second. Earlier on in the semester, we learned that gravity actually changes with height, and we came up with this equation where the gravity as a function of height is equal to this Newtonian gravity at the Earth's surface divided by 1 plus a over the radius of the Earth squared, and a is the altitude above the surface. So when the altitude is equal to 0, this converges back to g naught star. So let's just do an example of how gravity changes as you move up in the atmosphere or even out to space. So let's just say that the altitude of the International Space Station is 350 kilometers. One is the gravity on the space station. So we just plug it into this equation over here with 350 kilometers for A and 6,367 kilometers in the denominator. And you'll come up with a gravity on the International Space Station of 8.83 meters per second squared. So why do the astronauts experience microgravity if they're still experiencing, more than 8 meters per second squared of acceleration? The key is in the fact that there's an opposite force to gravity, which is the centripetal acceleration. So in this, if this is the Earth and the International Space Station is in an orbit around the planet, the curvature of that orbit imparts a centripetal force, and the centripetal acceleration is essentially omega squared r. Not the force, but the acceleration is omega squared r. And omega is the angular velocity, and r is the radial arm of that curvature. So if we know that the astronauts experience microgravity, which is essentially a net zero of gravity. In this case, the centripetal force has to be equal and opposite to the force of gravity in order to get that microgravity, which we know the astronauts experience. So how fast does the International Space Station have to be traveling at an orbit of 350 kilometers in order for that microgravity to be observed? In order to do that, you'll just set the two forces equal to 0, g of z minus the centripetal acceleration, omega squared r, set that equal to 0, solve for omega, which is your angular velocity, which is your g as a function of height, which in this case is 8.83 meters per second at the altitude of the International Space Station, divided by the radius, in this case, which is the radius of the Earth plus the altitude of the satellite, r plus a. Take the square root of that, and you'll get an omega 0.00114655 radians per second. In order to convert that into a tangential velocity, you have to multiply the angular rotation rate by the radial arm. And if you do that, you'll come up with 7,701 meters per second, or about 7.7 kilometers per second. And since we're in the United States and a lot of people have trouble with kilometers per second, that translates into a little over about 17,231 miles per hour is what's necessary in order for the space station to stay in orbit and the astronauts experience microgravity. So you can see that the angular rotation rate can have a significant impact on the effective gravity experienced by an object or a person depending upon that angular rotation rate. So our planet is actually rotating. It rotates 2 pi radians in 1 day. So that's 2 pi radians in 86,400 seconds, which gives you an angular rotation rate of 7.272 times 10 to the minus 5th radians per second. And at the equator, the centripetal force is essentially in the opposite direction of the gravitational force. So this is going to make the effective gravity felt at the equator less. As you move up to 45 degrees north, the radial arm is getting shorter, so the acceleration due to the centripetal force is going to be reduced. And by the time you get to the pole, their radial arm is equal to 0, and at that point the force of gravity is directly towards the center of the Earth, and it is not impacted by the rotation of the planet whatsoever. So there's going to be a latitudinal dependence on the effective gravity that is observed. So let's just take a closer look at that. If we blow this up a little bit, we have the Earth's surface about 45 degrees north. We have the gravitational acceleration, which is pointing towards the center of the Earth. We have omega squared, radius of the Earth times the cosine of the latitude, which is our radial arm. And that vector can be added into the situation, and you have the resultant vector g, which is the dashed line here. And you'll notice in this case that the resultant vector is going to have a smaller magnitude than the gravity that points towards the center of the Earth, and it's also pointing in a different direction. So the effective gravity, when you include the centripetal acceleration, gravity no longer points at the center of the Earth, and it weakens the gravity at 45 degrees north. So from this you can see that our effective gravity is going to be strongest at the poles, it's going to be weakest at the equator, and what actually happens in reality is that our planet is not a perfect sphere. The fact that the effective gravity changes with latitude has an impact on the shape of our planet. And up here I've drawn an exaggerated figure showing that the Earth is in fact a spheroid, and it bulges at the equator and is reduced at the poles due to the effective gravity that is being experienced at the surface of the Earth. What you'll notice here is that the force of gravity now is everywhere tangential to the, well, is orthogonal, basically a 90-degree angle to the surface of the Earth. So effective gravity is always going to point in the local minus k hat direction. So gravity, from my perspective here, is pointing straight down into the ground when I'm on a level surface. Now that direction is no longer pointing directly at the center of the Earth, but the Earth is deformed in such a way that local gravity points in the minus k direction locally. The impact of this, including the effective gravity, if you do the calculation at the equator, g naught plus the omega squared radius of the Earth. At the equator, the cosine of 0 is equal to 1, so you're just looking at the radius of the Earth. The effective gravity at the equator is 9.792 meters per second, and the gravity at the pole is 9.826 meters per second, for a difference of about 0.34%. So why do we worry about 0.34%? Because we're talking about gravitational potential energy, and if my potential energy is off by 0.34%, that error is going to propagate in everything that happens after that. So we want to have the energy of an air parcel as accurately as possible. Now the effective gravity, if you want to delve into this a little bit deeper, is actually impacted by a function of height as well, because this equation over here assumes that the Earth is a sphere and that the radius of the Earth is equal everywhere. But that's not true. You can see this for the spheroid up here. In reality, the radius of the Earth from the center of mass to the pole is 21 kilometers less than the radius at the equator. So another thing that you would have to do in a computer model is to include the fact that the Earth is not a sphere, to get the, and include that difference into the local gravity as well. Because we want to make sure that we have the most accurate gravity for that gravitational potential energy that we can possibly have. So we have to take into account the non-sphericity of the planet. We have to take into account the angular acceleration, giving us a centripetal acceleration to get our effective gravity.